morning, everyone. I hope you guys had a good break and good 2 days vacation, kind of, and you had the chance to start looking at your the review for your exam. And if you have any questions about the review, please come to my office hours and I will help you with them. All right. So before we start today, I would like to make a comment about the quiz and then we proceed. Usually I make a comment about the question that the answer I did not very much like your answers. It means you had some mistakes in it. So it was quiz number 9, the last question. True or false? So I told you if you have two series, if sigma AK, sigma BK, they are positive. So crucial, I told they are positive, and the AK is always less than BK. So is the following statement true or false? Sigma AK diverge, it means the smaller series, if sigma BK diverge, then sigma AK, the larger series, must diverge. So if the largest series diverge, then the smallest one must diverge. And the question that if true, justify, if false, give an example. Okay, so whenever something is false, to give an example. And it was false. That's not a correct statement. So if the smaller one, if the largest one go to infinity, the smaller may or may not. Give me an example. What type of example you gave? And so a lot of you put false, but they did not give me a correct example. The example is, how can this be false? True means that if this diverge, the smaller diverge. To show me it's false, it means you have to give me an example where the sigma BK diverge, but the smallest one converge. So false, the example should be such that the largest one diverges. That's what it means in example. How can this be false? If you can give me an example where this one diverge, but the smallest one converge. That's how the example. So the example is, this property is satisfied, which we usually call the hypothesis is satisfied, but the conclusion, which is the sigma AK, this one should not be true. It means this one converge. And the example should work. So I had some students, of course, they gave me a good example. So let me give you a very, very easy example. So the one I put on my solution, I'm going to take AK to be 1 over K squared. It is positive because I said my hypothesis that things should be positive. BK, very easy. I'm going to take BK to be 1. Very, very easy examples. So now the property is satisfied. Everything is positive. It's less than 1. Basically, 1 over K squared is definitely less than 1. 1 over 2 squared, 1 over 4 squared, they're all less than 1. And now what's happening? The largest series is basically 1 plus 1 plus 1 plus etc. This definitely diverges. However, the smallest one converge because it's a P series with P equal to 2. Okay, so that's the type of example you have to give me. To show me it's false, you give an example where the hypothesis is satisfied, it means sigma BK diverge, and the conclusion is false. That's how the statement could be false. Okay, any questions? Okay, so for those who got it, so a lot wrote false, but they gave me absolutely an example that really does not work. All right, so today we're gonna go back to Taylor polynomial. I started them last time, and we're gonna work with them a little bit. We're gonna work with them today. So let me read this. You guys, if you're taking notes, you have this already. So Taylor polynomial is the idea of polynomials, those simple functions that approximate another function. So what are they? So Taylor polynomial. Let f be a function with f prime, it means first derivative, f double prime, second derivative, third derivative. For all the derivatives are defined at a point A. So this is f prime, that's the second, that's the nth derivative. The nth order Taylor polynomial of f with its center at A is given by, so that's the formula for it. Pn of A equal f of A plus f prime of A times x minus A. And last time I told you, what does this piece represent as far as the function is concerned? Anybody remember? What does those two terms represent graphically? Back to you now.
That's the equation of a tangent line.
That's the equation of a tangent line. So the first two terms are basically the tangent line. Plus, that's the quadratic approximation. And up to here, you have a polynomial of degree 2 that has for property that at A, the value of the polynomial is the same as the value of the function. The derivative of the polynomial is the same as the derivative of the function. The second derivative of the polynomial is the same as the second derivative of the function. It means that the polynomial will have the same concavity. But then we can approximate it by a cubic polynomial. And what mathematicians were able to prove that the best cubic polynomial to approximate the function is the one obtained by this formula. And then we can approximate it by a fourth degree Taylor polynomial, a fifth, a nth degree Taylor polynomial. So these are equations of an nth degree Taylor polynomial that will approximate the function very well. And in sigma notation, we write this as sigma k equals 0 to n. So what changes here is the degree of the derivative, the denominator here, and the power. So it's the derivative order k at the point A, that's my base point, over k factorial x minus a to the power k. K equals 0 to n. Okay, so now we're going to go back to the function I started working with on Saturday, last Friday, and we take another example. Okay. Right. So let me take the function to example. Let's take the function f of x equal the square root of x. And find the linear, and this is what I did last time. I just write the answer. Find the linear and the quadratic approximation of f. Quadratic approximation, which in other words, find Taylor polynomial of degree 1, that's the linear, and Taylor polynomial of degree 2, that's the quadratic. And the quadratic approximation of f center at a equal to 1. I think that's what I gave you last time. Yeah. Okay. So what's the linear? Linear, it means the first degree Taylor polynomial that was f of a plus f prime of a x minus a. That's the formula. It means f of 1, the value of the function at 1, plus f prime of 1 times x minus 1. So last time we got the following. I will not repeat it because it's easy. F of 1, the value of the function at 1 is 1, plus f prime of 1 is a half x minus 1. So that's the linear approximation. That's basically the tangent line. Okay. Now the second degree Taylor polynomial is, the reason I'm writing them because I want you to start basically memorize the format. The second derivative at 1 over 2 factorial x minus a squared. So it's equal to 1 plus f prime of 1 is a half x minus 1. And this term turns out to be 1 over 8 x minus 1 squared. And that's the second, the quadratic one. Okay, so that's what we did last time. And then we did the following. I asked you is use P1 and then P2 to approximate the value of the function square root of 1.5, which is basically the value of the function at 1.5. Now, before we do that, let me share with you a little bit the screen so we can see graphically P1 and P2. So I'm going to share the screen a little bit with you to do that. So share screen. Okay. All right. So this is the function. I'm going to input the function here, which is the square root of x. My point is 1. The point is 1, and I'm going to share that. Sorry, I didn't input square root correctly. Okay, here we are. All right, so that's the square root of function, the green graph. And now Taylor polynomial of degree 1. That's the tangent line. That's exactly the tangent line. It means what we did here. So the equation of this tangent line is basically this piece right there. That's 1 plus a half times x minus 1. So as you can see that the tangent line approximates the function near 1. The approximation is absolutely near 1. That's what the center at 1, the importance of it. As we move further away from 1, this is definitely a bad approximation. So this approximation works very much near 1. Now I can move on to Taylor polynomial of degree 2. So Taylor polynomial of degree 2 is basically a parabola. That's my quadratic approximation. And it's definitely hugging the function, so better than the first degree. So if you go back to the first degree Taylor polynomial tangent line, when you go to the second degree Taylor polynomial, it's absolutely closer to the function. That's really the idea that we are building. Polynomials, that they are closer and closer function. This second degree has the same concavity of the function. It's quadratic, it's a parabola. It has the same tangent line, and it agrees with the function at 1. And at the same time, it has the same concavity. So that's really what characterizes this second degree Taylor polynomial. So I'm going to use the polynomial to approximate the value of the function. This is 1.5 down here. I'm going to plug it into the equation of the polynomial, and I'm going to realize that the value obtained by the polynomial and by the function are relatively very close to one another. That's what we're going to mean by approximation. Okay? So that's really the idea. And so how can I approximate? So we're going to check. We evaluate the polynomial at 1.5. It means that we plug in 1.5 into the expression here. That's okay. And now we get an answer, which is basically you can pick up your calculator and get it. And I got 1.25. Okay, so this is an approximation of the function. So this is the square root, and that's my approximation. We're going to use them to approximate the value. Now, when we take the second degree, we should get a better approximation. So if I take the second degree, we get 1 plus a half, 1.5 minus 1. The first terms are the same. We're adding the quadratic terms. And we pick up our calculator and we get 0.25. 0.5255, 0.2, no, sorry, I get 1.21875. Okay, now the actual value, it means the one we pick up. So that's the actual value. It means the one I'm picking up from the calculator. So the actual value is actually 1.2247. So we can see that, of course, the second degree approximate better than the first one. And it's not too bad. I mean, I only use very few computation to be able to approximate the function. Now let us move on. What if I take the third degree and the fourth degree? So for this problem, I'm going to do also the third and the fourth so we can have a good idea how to compute them. So my question now is the following. See, find the third and the fourth degree Taylor polynomial. The third for the same function at the same point. Polynomial of the same function. So we're going to approximate it better at the same point. Is my approximation work only or near that point? All right, so I will write P3. And then I will write P4. I just write them and then we compute them to see how the writing is. It is f of 1. That's the base point. Plus f prime of 1, x minus 1. Plus, see how it works. Second derivative at 1 over 2 factorial x minus 1, that's my base point, squared, plus the third degree. It works like this. You take the third derivative at 1 over 3 factorial x minus 1 to the power 3. That's the third degree Taylor polynomial. Now, how does the fourth degree? Fourth degree is, again, f of 1 plus f prime of 1, x minus a. The second derivative at 1, x minus 1 squared. So that's really my a. My base, sometimes I like it, my base point is the point near which we're doing the approximation. The third derivative at 1 over 3 factorial. X minus 1 to the power 3 plus the fourth derivative at 1 at the base point over 4 factorial x minus 1 to the power 4. So that's the formula, and now we're going to evaluate them. So to evaluate whether it's the third or the fourth, I need f of 1, f prime of 1, the second derivative at 1, the third derivative, and the fourth derivative. So I'm going to start by evaluating this, and then I just plug them into the formula. So let's do that. My function is the square root of x. F of 1 is 1. Okay, now the derivative. So x, of course, to find the derivative, I rewrite it as a power. So f prime of x is a half x to the half minus 1. It means f prime of 1 is a half. Now the second derivative is a half times that minus a fourth minus a half minus 1 minus 3 half, and then I gave you a simple point right now, is minus 1 over 4. So I need up to the fourth derivative. So the second derivative, the third derivative, it means I keep differentiating. Equal to minus minus is a plus. 1 half times 3 half, it's 3/8. X to the minus 3 half minus 1 minus, it means the third derivative at 1. So it's just tedious computation. And finally, the fourth derivative.
What is the power for the third derivative, say?
Minus 3 half minus 1. Give me minus 5 halves.
Okay.
Okay. 5.
All right.
Thank you. 5. My mistake. Okay. The fourth derivative. So that's the notation for the fourth derivative. You put 4 between parentheses. That's the fourth derivative. Plus minus 3 times 5. That's going to give me 15. 8 times 2, 16. X to the power minus 5 halves minus 1 minus 7 halves. It means that the fourth derivative at x equal at 1 at the base point minus 15 over 16. Now we evaluate the pieces. Now I'm going to write up my polynomial. What's P3 and what's P4? Okay, all right, so that's P3. Will be f of 1, 1, plus f prime, x minus 1, plus the second derivative, which is basically minus 1 over 4, divided by 2 factorial, x minus 1 square, plus the third derivative, divided by 3 factorial, x minus 1 to the power 3. So that's the third degree Taylor polynomial. Now, of course, no, we don't like that. As I said, let us simplify that a little bit. It means what P3 equal 1 plus a half x minus 1 minus 1/4 over that is going to give me 1 over 8 x minus 1 square plus 3 factorial is 1 times 2 times 3. It's a 6. I will have 3 over 8 times 6, which is 48 x minus 1 to the power 3. Okay. So finally, P3, because we can simplify a tiny bit, that's my third degree.
I have a question.
I'm listening.
So when you divide by a factorial, it just cancels out. So 1/4 divided by 2 factorial, it just becomes 1/8.
Yeah, because it's 1 over 4 divided by 2, right? That's 2 factorial. Because 2 factorial is what? Is 1?
1 times 2.
2, which is a 2, right? So it's going to give me 1/4, basically divided by 2. It means, what am I doing? Yeah. All right, it's just algebra at this stage. And this will give me 3, and this is going to give me a 1, 6 x minus 1 to the power 3. Okay, so that's the third degree. Now, the fourth degree is basically the third degree. You add one term to it. That's important to be careful with that. So what's the fourth degree? The first, the third, degree, but you add something. You add the fourth derivative, which is, so we add the fourth derivative at 1 over 4 factorial x minus 1 to the power 4. Okay, so the fourth degree is exactly, so we're adding the same term. So it's the third, but you add this term to it. That's what the fourth degree is about. So finally, you do the math and we get the following. It's going to be 1 plus a half x minus 1 minus that plus this. And then the fourth degree. The fourth degree was minus 15 over 16 divided by 4 factorial. 4 factorial is 1 times 2 times 3 times 4, 6 times 24, x minus 1 to the power 4. And this gives me the 4th degree Taylor polynomial, okay? Which is, as we will see on the graph, it actually approximates the function better than the first, better than the second, and better than the third. So before we move on, let me share the screen with you. And again, see what's happening graphically. Okay, so graphically, this is the 1st degree. Sorry, the green is the function. So the 1st degree is nothing more than the tangent line. The 2nd degree is the parabola, which is look closer than the function. The 3rd degree is a polynomial of degree 3, which is, it's not a parabola anymore. We know degree 3 is look like this S shape. So it's not really a parabola, but it should be closer to the function. Now of degree 4, degree 4, we get even closer and closer to the function. And the idea is that if I go degree 5 and degree 6, as you realize, the higher the degree, the closer we are to the polynomial. 8. Now, we are doing the approximation near 1. And as you realize, beyond 2, the polynomial do not approximate the function anymore. So the approximation is not for all x's. The approximation is going to be near the point 1, around the point 1. Actually, it's going to be between -1 and 1. Between 0 and 2. But the approximation is near 1, it's not farther away. So after that, if I want to approximate the square root of x at 3, for example, I should take a equal to 3. So if I want to approximate it near 3, so I take basically, this is the tangent at 3. No, this is the tangent at 3. I was skipping one, this one. Tangent at 3, tangent at 2, and so on and so forth. So if I want to approximate near 3, I take the base point to be 3. If I want to approximate near 1, I take my base point to be 1. So the base point is near which point I need to approximate the function. Now, the last question is D, whatever. Use the 4th degree Taylor polynomial to approximate the value of the function at 1.5 or the square root of 1.5. Okay, so use the 4th degree to approximate. All right, what does this mean? It means what we're saying is that the function at 1.5, that's really what I am saying, is when I approximate it by the value of the polynomial at 1.5. Okay, that's just to give you, it means that if I plug in at 1.5 into the expression of the polynomial, I should get a value very close to the actual value of the function. So this is equal to what? Means I plug in 1.5 into the expression of the polynomial. So I plug it in here. So 0.5 minus 1 is going to be 0.5 minus 1 over 8. So I'm just plugging in into the expression of the polynomial. 0.5 to the power 3 minus 15 over 16 times 24. Now I know we can simplify this, but you guys can do that to the power 4. So it means that square root of 1.5, we're approximating it by, we plug in 0.5 into the expression here, and we pick up our calculator, and I did that. I got 1.22421. Okay, so use P4 to approximate this. So that's really my good approximation. So the last question is, so 2i, find the absolute value of the error in the approximation. So find the absolute error in the approximation. What do you think they mean by that? What do they mean by the absolute error?
Like how far off we are from the actual point?
Exactly. It's how far are we are, but in absolute value, because we could be less than the actual value or more. So find the absolute values. The absolute value is the error. It means the value, the actual value of the function, which is for us now, what we pick up from the calculator. That's what the actual value minus the approximate value. That's what the error is. So this is the actual value. And this is the approximate value. It means basically what I'm going to evaluate is the actual value, which is there, minus our approximation, which is 1.22421, which is going to be equal to. Now this one, I'm going to pick from the calculator. So I'm basically going to go back to my calculator here and evaluate that, which is 1.5. I'm going to, sorry, I should put the absolute value, but we can do that later. And 1.22421. That's really what I am doing. So I'm getting 0.00053487. So the error is very, 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 very small, as you realize. So if I use the fourth degree, the error is very small. Okay. Now, of course, you're asking me, why do we need to approximate the square root of 1.5? I mean, the calculator gives us the value. And the correct answer, or the honest answer, is what we will be approximating is not really the value, even though we're going to do that as a practice. What physicists approximate is the function as a whole. So the way physicists will use this is in the following context. They will say the square root of x near x equal to 1, near x equal to 1. That's how we're going to, actually in real math, they use it. The square root of x, which is a very complicated function, I can approximate it. So instead of looking at it as a square, I can approximate it by lines. We can do a linear approximation. So instead of working with the square root, I can work with this. If I need a better approximation, we use the quadratic one. That's basically how it is used. So physically in their head, if they're working with the square root x, they basically get rid of the square root x and they work with the polynomial. That's how mathematically it's being used, and that's how the physicists use tremendously those ideas, and they use it a lot. They use quadratic most of the time to approximate function. And then they said, okay, but I need something better because I'm doing very accurate. They say, okay, I can take the third degree Taylor polynomial. So I can view square root of x as a polynomial instead of viewing it as square root of x. Polynomials are easy to work with, easy to differentiate, easy to integrate. Anything you want, you can do it with polynomial. You cannot do it easily with the square root of x. So that's really how mathematicians and physicists work with those ideas. Okay. In this class, we're doing this just to help us a little bit basically understand what's really going on. All right. Okay. Questions before I go on? Okay, so we're going to do one more example, and then we kind of generalize slowly this idea. So second example is, let us do a simple function. Example number 2. Okay, and my example is let f of x equal, for example, sine x. Okay, hard function to deal with. And my question is, question number A, find the third degree Taylor polynomial Taylor polynomial of f centered at a equal to 0. Okay, Sometimes those polynomials are called Maclaurin polynomial when the center is a equal to 0. So first I'll write it. I'll write it so we know exactly how to write it. Is the value at 0. That means I'm doing the approximation near 0 plus f prime at 0 x, because a is 0, so it's going to be x now. F double prime at 0 x squared. A is 0, so be very careful with the center. And then the third derivative at 0 times x cubed. So now to be able to find this, I need to find f prime, f double prime, and the third derivative. So we do that easily. F of x is sine x. F prime is, so f of x is sine x. It means f of 0 is the sine of 0, which is 0. F prime at 0 is cosine of 0, which is a 1, and then I keep going. The second derivative at x, derivative of cosine is minus sine. So it's just basically computing derivative, which is again is 0. And finally, the third derivative. It's minus cosine. It means the third derivative at 0 is minus the cosine of 0, which is minus 1. And now P3 of x equal. Okay, now I apply it. F of 0 is 0. It's gone. F prime of 0, it's 1 times x. It's x. That's the tangent line. That's the linear approximation. The second derivative at 0 is 0. So basically, it's going to be 0 over 2 factorial x squared. It was going to be 0. And then minus the third derivative. Oh, sorry. Oh, please, 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 please. I did a stupid mistake. I shouldn't. Okay. Now, 1 over 3 factorial x cubed. So it means it's equal to x minus 1 over 3 factorial x cubed. So that's the third degree Taylor polynomial. Okay. So for us, which means, it means that near x equal to 0, that's really what it means. The sine of x could be approximated by x if we want a linear approximation, which is work if you are very, very close to 0. If we want an approximation, which is we can help us move away a little bit in 0, that's a cubic approximation of the sine. So we can view sine basically as the third degree Taylor polynomial. If I need better approximation, I add more term. I take the fourth degree and the fifth degree. Again, I'll share the screen one last time with you, and I want you to see those polynomials so you can interact with them. So that's we share the screen. Okay, I'm going to take the sine function. The sine. My center at 2, at 0. It means I'm approximating near 0. And here we are. The first degree Taylor polynomial, f of x equal to x. This is the tangent line. That's the first degree. And you can already see that the sine x and the x are close to one another near 0. If I want a better approximation, now in this problem, it happened that if n equal to 2, because the second derivative at 0 is 0, so there is no quadratic. That's why I had to ask for the cubic approximation. You can see that we're having a much better approximation of the sine. So I want you to compare 1 versus, 2. So the second, third degree Taylor polynomial is absolutely better approximation. Then I can keep going. I can do 5. You can see how better the approximation is. I can do 7. 9. You can see, remember, the red is the polynomial. So the red one, that's the polynomial. The green is the actual function. And you can see how better my approximation is. And then I can keep going. I can keep going. I can do 11. And the more polynomial I take, at some point, as you realize, you barely can see the difference. This is the polynomial of degree 11, 15 in this case. So that's the approximation. And that's the actual function. And you can see how better my approximation is getting. And the more polynomial we get, the better the approximation. So you can see now the approximation is getting better and better and better. Okay, so that's really the idea of Taylor polynomial. Okay. So now I can ask you very much, use a polynomial to estimate. So use the third degree polynomial to estimate or to approximate sine, let us say, of 0.4. Okay, so I'm still 0.4. I'm not really farther away from 0, even though, as you realize, I can, from the graph, that even if I am like 1, I can still do that. So estimate the sine at 0.14. So the Taylor polynomial tells me that sine at 0.4 could be approximated by the value of the polynomial at 0.4. Means I plug in 0.4 into the expression of the polynomial. To the power 3. So it means that the sine at 0.4 is almost equal to, now I don't think I evaluated that term at all. So I can just plug in into my calculator and I will get 0.4 minus 0.4 to the power 3. 0.4, if anybody got it faster than me, which is usually you guys do it, divided by 6. So I'm getting 0.3893 repeating. So now let's see the absolute value of the error. So let's see how good is our approximation. If the answer is big, it means what I'm doing is nonsense. So now the error in the approximation. It means I take the actual value, so now the error, minus my approximate value. And I evaluate this just to have an idea how well I am doing. So I basically plug everything into my calculator and I proceed, and I'm getting 0.00085. So you can see how well we are doing. Okay, so we are doing extremely well at 0.4, and that's really the error. So which really tell me basically that, oh, well, since they are so close to each other, why not work with that instead of the sine? Why not approximate the sine by this polynomial and actually work with it? And that's what I repeat, that's what people use, those approximations. They physically, they get rid of the sine and use the polynomial. Now,
I have
of
a
course,
question.
please go ahead.
So the more that you use, like the more P3, P4, the more that you use, the closer your value is to the actual value.
Absolutely.
Okay.
Absolutely. That's the main idea. More term you take, better the approximation.
All right.
Remember the picture, the graph I showed you? Do you remember the graph? Let's share it one more time. Watch the graph. Okay, this is the sine. This is the first degree. Do you see it?
Yes.
Watch if I take the third degree, which is a better approximation.
Oh, third degree, definitely.
You see? First,
Yeah.
watch. Sorry. Watch, that's linear. Now it's quadratic. I mean cubic. If I take the fifth degree, that's what's happening. Do you guys see it? Actually, this graph gives you the formula, but I don't care. If I take 7, so I add more term, that's the range. So it's actually even closer. And then I keep adding. If I take the 9th or whatever, the 11th degree, you see how far is the range that the function approximated with. So 1, we only approximated very close 0, but now even when I take 11 degree, that's the formula that you guys will memorize eventually, it should be between -5 and 5, and I'm still very close to the curve. This is the polynomial, that's the approximation, and the green is the actual function. And you can see that you can barely differentiate graphically between them because the error is so small, you can barely distinguish between the green and the red. The red is the polynomial, the green is the function. All right, so the last example with that, so as I said, there are theorems that give you on the error, but we will not go through that. We just have to understand the basic idea. The last problem I will do, mainly because a lot your homework is around those lines. The question is the following. Example number 3. Okay, so suppose you're given the following. You're told that the second degree Taylor polynomial, so this time I'm going to give it to you of f of, even though it's very easy for you to evaluate, of f of x equal ln of 1 plus x is given by. So that's the second degree Taylor polynomial. So I'm giving it to you. So that's the quadratic approximation. Okay, and you can do that. I mean, this is really easy to come up, but let us say I give you the second degree. The question is, use P2 to estimate ln 1.08. Okay, so question number 1 to you. If they tell you the second degree Taylor polynomial f of x equal ln of 1 plus x is given by that, what do you think the A is in this scenario? It means what's going to be the center. It means near which value are they doing the approximation? Back to you.
0.8.
It'd be 0.
0.8.
No, the first answer, the second answer was correct. A equals 0. Okay, because how does the Taylor polynomial is? If you are approximating near A, it's a polynomial in x minus a squared, x minus a cubed. Now, since I gave you x squared, x cubed, it means they are giving you the approximation where a equal to 0. All right, so first this is the Taylor polynomial centered at a equal to 0. So that's really the center. Now, question number 2, I want to use it to estimate ln of 1.08. So actually, before I write that, so this means that ln of 1 plus x is almost equal to, that's how I want you to understand it, almost equal to x minus a half x squared, near x equal to 0, near a equal to 0. Okay? So near a equal to 0, near a equal to 0, ln of 1 plus x is approximated by this quadratic. Very, very important idea. I mean, how messy is working with the ln? How easy it is to work with this polynomial. Now I'm going to use this to estimate ln at 1.08. So what value of x I am taking?
0.08.
What?
0.08.
Exactly. No. Yeah, absolutely. It means x is 0.08. All right. So very careful. So I want you to estimate ln of 1.08. It means my x is 1.08. So it means the 1 plus x here is the 1.08. It means my x is 0.08. 0.08 is close to 0. So the estimate makes sense. Okay, so it's going to be 0.08 minus a half 0.08 square. And then it means ln is almost equal, and then the rest is really easy. There's nothing into it. Minus 0.08 square divided by 2, and this gives me 68, unless I'm doing something wrong. Not to check I'm doing not something very bad. I say, okay, what's ln at 1.08? Yeah, that's the approximation. Okay. Now, the last question is use P2 to estimate. Still, I am near 0. So suppose I want to estimate ln of 0.95. Okay. So again, the same estimate. So 1 plus x is x minus a half x squared. Now I want to estimate ln of 0.95. What is the x in this case?
Negative 0.05.
Negative 0.05. How did you get it? Because we're not going to guess, basically. We're going to find it. How do you go get it?
The 1 plus x equal 0.05.
Exactly.
Or
I want
0.5.
the 1 plus x to be the 0.95. It means I need my x is, because 0.95 should play the role of 1 point x. So it means my x is 0.95 minus 1. That's really how my x is. So it means my x is minus 0.05. And now I can evaluate this. So it's going to give me, means I'm plugging in minus 0.05, which is near 0, because it makes sense, because all my approximation is near 0, minus a half times minus 0.05 square. And now the rest is done with done, because the rest is simple. Minus 0.05 minus a half times. And unless I'm doing anything wrong, it means this is almost equal minus 0.05125. Now estimate the error. It means you find the actual value of the ln minus this, and you should get a very, very small number. Actually, if I evaluate ln at 0.95, I'm getting minus 0.0, sorry. I'm getting the actual value minus 0.05129. That's the actual value. Our value minus 0.05125. So they really agree to up to 4 decimal places, and they start disagreeing after that. So the error is going to be less than 10 to the minus 4, something like that, right? And graphically, we can see all this graphically, and you can see how the ln of 1 plus x can be viewed basically as this polynomial, a very good quadratic approximation. All right, that's it for today. Your homework is on MATLAB. Please do it. Don't be behind, because your exam is on Friday, and it's going to require all this material. What I'm going to do now, and what I will be doing tomorrow and the day after. All right. Okay. Any questions? Class is dismissed. As usual, if you have questions, please remain.